Yeah, back when remember our department, Sam Hudson, he used this stuff.
Does he still work at Conoco?
Yeah.
He's a younger guy, right?
He is, well, compared to the Title IX area here, you know, prejudice against old people. Yeah, he just started like 3 years ago.
He worked for Conoco Phillips. So yeah, he knows his stuff. He's co-taught this class in the past.
Yeah, so he'd be a good guy to talk to about reservoir modeling. So is this live? Okay. Bill, if you're watching this, we miss you, okay? And the class really misses you, because otherwise you'd be, okay? We miss you one way or the other. So, what I want to do is finish up. So you'll be ready to start on Tuesday with Bill Peach's portion. You'll still see me. I'll be coming back for cameo appearances. I'm going to sit on the class because I always learn something when Bill is teaching me now. So to review, log. So going back to the beginning, this track is the pathology correlation part of the log. Okay. This is the depth track. That's kind of trivial here in the middle. What's missing? There's a middle track. It's not shown here. It'd be right here.
The resistivity.
The electrical resistivity, which is telling you something about the fluid properties. Obviously, resistivity can be correlated roughly to salinity. A lot of times you think of the matrix as being infinite resistivity, but that's wrong in the case of what? If the matrix isn't resisting, it's conducting, then what kind of matrix would that be? Geologists can help you out here. What type of rock? Well, it's something that conducts electricity would be low resistance. Right? So that's, yeah, iron, yeah, or my favorite substance, stainless steel, right? But not a likely scenario, but something that the geologists know. Geologists help me out. What mineral has electrical conductivity? Clays. Clays have a surface charge, okay? So clays are a real problem in oil exploration in the sense that they invalidate your assumption that the matrix is just marbles, or that it's just something that is of infinite resistivity compared with fluids. So the point is, when you're talking about that middle track, resistivity, you've got to be careful, because if you're in a shale, for example, well then the resistivity is a function of both the fluids. You have lots of fluids in shales. You have the original salt water, or salt water that's coming there later, and the matrix, which is largely clay. Okay. So in a case of a classical reservoir or conventional reservoir like a sandstone, well then the resistivity is just telling you something about the fluids. Which, if you're going to use resistivity for correlation, which you almost always do, you have to be careful. What are you actually correlating? Well, you're actually correlating the fluids and the matrix. So be careful that you're just not slipping into this false assumption that, well, I'm just thinking about the matrix. The sandstone is always going to look the same. Well, if you change the fluids in the sandstone, it's going to look completely different, and therefore you cannot use it for stratigraphic correlation as easily. Okay, so that's the middle track, and then this is the right track, rightmost track, and this is where we left off. So what is this? So the PHI stands for porosity, so this must be the porosity track. Okay, so kind of to think of it in a reasonable way, you can think of that, well, I've got something about the lithology in this track, the middle track is kind of the fluids, electrical resistivity, and this is storage. How much can I get into or out of the reservoir? Into, if you're talking about carbon capture and storage. Okay, so that's where we left off. Now, the density porosity log is one of three types of porosity logs, two of which we'll talk about. We'll talk about a third one later on in the semester when we get to that point. The density porosity log, well, it measures density, obviously, but you get two parameters as opposed to, say, one that you get from, say, the gamma ray log or the SP log. So what are those two parameters? They're actually abbreviated here. Remember what they are? You get two things. Remember what they are? What do you actually measure? The simplest thing to understand is, well, if it's a density log, well, you're probably going to measure density. So this RHOB is just supposed to make you think of something like that, rho B. Okay, so typical symbol for density. So you get density. What are the units? 2 to 3, so that's 2 grams per milliliter to 3 grams per milliliter. So 3 is obviously denser than 2. Okay. Obviously, okay. So you see two curves here. You see a solid curve, solid black curve. And again, where's 0? 1, 2, 3, 4. So 0 is right here. Okay. So you get two curves. The black one is actually density, right? So that's the real number. Real in the sense not mathematically real number, but that's the actual measurement. Okay? And then what's the dashed line? What's the long dashes here? That's the porosity model. Okay, that's the model porosity. It's assuming what? So you got to assume two things. This is what you measure, and then what do you have to know? The fine print. You got to know this, the density of the matrix, often abbreviated like that, rho MA. And you make an assumption, that's why this is over here, to tell you that a limestone matrix was assumed, so that the matrix condition here was 2.71 grams per milliliter. Okay, just kind of review what we did last time. But then, what about the fluid? Then there's also the fluid assumption. What's that? Well, that's kind of easier because that's derived from the drilling fluid. You know something about the drilling fluid. It doesn't actually tell us on this law, but if it were fresh water, then this would just be 1 gram per milliliter, right? That'd be easy. Okay. If it's salt, a little bit higher, maybe 1.1. If it's oil-based fluid, maybe it's not oils. Not all oils are the same. There's different proportion of oil and water, obviously, but maybe 0.85 grams per milliliter. But it makes a difference. Okay. So that's the portion of your log that relates to density and porosity. So there's your model porosity, and there's your measurement of density. Now, what's the other thing you get? These two are related, so that's one thing. So what's the second thing that's on here? This PEF stands for photoelectric effect. And you see the scale goes from 0 to 10. And in another class that we'll do next year, 521, we get into great detail of how the photoelectric effect works, and which is a physics problem, obviously, and how do you measure it, and a Borehole. But suffice it to say now, it's a number that gives you information about the elemental lithology. What does that mean? The elements was making up the rocks. Okay, so we talked to, so I assigned you each a number. Do you remember your numbers for your minerals? So who had dolomite? What's dolomite?
3.1.
So that's 3.14.
1.4.
And units are barns per electron. I'm not going to write that down. It's too cumbersome to explain, but let's say that's our number. Okay, limestone is what? Who had limestone?
5.08.
5.08. And then what would be the other one? Yeah, sandstone or quartz. Somebody had that? Remember it?
1.81.
Yeah, 1.81 sounds familiar. Okay, so those are your three numbers. Now these are kind of magic numbers. Magic in the sense that they can actually pull you out of a problem of interpretation. Okay, so the example we looked at here is that this is looking like what? So here's 0 to 10 on our scale, and we're trying to figure out what type of rock this is. The gamma ray is, well, that's just simply telling us it's kind of clean. It's not terribly helpful. Not totally clean. That's cleaner still. And it's what? 0, 1, 2, 3, 4, 5-ish. Right? So that's kind of giving you an idea that it's limestone. And then where this helps is that, well, dolomite, you said that's 3.14, so 0, 1, 2, 3 is right there. That looks like dolomite. Now these are very close to the actual zero porosity condition values because what's our actual porosity? It's very low. These are tight rocks. You're not going to get much out of these rocks. Okay. So if my porosity, it's kind of a quiz, right? If my porosity actually was up over here, if this porosity moved over here, how would those curves move? How would the PEF curves move? What would they change? See what I'm asking? If you increased your porosity, therefore you're replacing the dolomite or limestone with water or oil or something, how would it affect these curves? Do they change? Do they move to the right? Do they move to the left? You see what I'm asking? Yeah, because I'm replacing some of the mineral, or rock, but in this case mineral, with fluid. And fluids typically have a lower PEF. So these would also move that way. Not as much as that, maybe. Okay, you have to have an awful lot of porosity. So you have to be careful with those curves. Anyhow, that's kind of a summary of what we did. And to just sort of skip to where we stopped last time, this is the model solution. So this symbol here with the non-right angle lines to it, light blue, that's dolomite, dark blue, it looks like bricks, that's every geologist thinks of limestone. I'm not even sure where that came from, okay, but it's archetypal in people's minds, right? And then the purple slashes, we didn't talk about that one yet, but we talked about it last time. That's our unusual rock, right? Unusual, or at least it stands out. Because what kind of porosity do we have here? We have minus 15%, well, that doesn't mean anything, right? Well, it does. It actually means a lot, but it doesn't mean it's minus 15%. It means that this model is wrong. It means that our rho MA was too low. It should have been higher. It should have been 3 grams per milliliter about. And that would then shift this over to actually 0. Okay. So then we just have to remember that, well, a common rock type that has a high density that we might find in this type of setting would be anhydrite, which is what? Anhydrite is just a name for, what's the chemical formula?
CS4.
Yeah. So it's like gypsum, which most people heard of gypsum or drywall material derived from that, without the water. Okay, so it's very dense. You take the water out, it becomes denser. Okay, so that's what all this stuff is. Now, for a petroleum point of view, just as an aside, why do we actually care about anhydrite? I just came, some of us, at least I just came from the talk where anhydrite was being talked about a lot, in associated with limestone reservoirs.
Anhydrite is a great seal.
It's a seal, so that's not the seal at the 0, right? It seals off your porosity. So it's very important in that sense because it's a perfect seal because it flows. It's like salt. Salt's a very good seal. So it has no porosity and obviously no permeability. So that's where we left off last time. So just kind of like to review. So let's skip ahead to where we belong. Here's a test. So yeah, we're not going to have a test, but let's say we have a test. Here's a log going back to our original, just our gamma ray log. Where's the reservoir? Now, what's also shown is a caliper log. We haven't talked about caliper, but it's in a sense simple in that it's just measuring the width of the borehole. But you see where our gamma ray is? A little bit hard to see maybe, so I'll trace it out and take out some of the detail. Okay. And here it is again. I've just taken a really nice log and made it very sloppy looking. Okay, but now you can see it. So where's the reservoir, the gamma ray log? Well, back up. What first question do you always ask? What is the log actually measuring? So here's our scale, 0 to 150. It's always going to be like that. So 150 means if you had something over here, if my log is over here, what does that mean? You have lots of potassium, uranium, or thorium. Okay, so maybe it's a shale if you have that type of environment. You have lots of potassium that's associated with clays, that's a principal component of shale. And then this would be what? Now, this is a trick question. It's clean, less potassium or clean. Okay, now is it a reservoir? I don't know. How much potassium does this thing have in it? well, I don't actually know, but let's say it doesn't have that much. So this could simply be that, but it's not a reservoir. Or it could be anhydrite. How much potassium does anhydrite have? We looked at an example last week. Or halite, salt. It doesn't have any, it would look very clean. So where's the reservoirs a little bit, you better not say something right away. The usual question to ask when you ask the question is, well, I think I need to see another log, right? So the knee-jerk reaction is simply say that's the reservoir, but I showed you an example where that would not be the case, so you would have made a mistake. So here's an interpretation. I took this from a publication. It's a good example. They're interpreting this. The SH probably stands for what? Shale, S-H-A-L, so that's probably a shale. And then what would if you had a density porosity log, what would it look like? Okay, well this is what it would look like. It's an actual log. So that when you see this, you'll notice there's actually two curves. So we're going to talk about this next one. We're going to talk about this dashed one next, the neutron porosity next. Right now we're doing this one. What does this mean? When they put sandstone in big bold letters, what's that supposed to mean? That it's all sandstone? They're giving you the answer?
Matrix assumption.
It's a matrix assumption. And what that's telling you is that your rho MA used in your calculation is that number. Well, oops, that's not what I want to do. We're going to use the eraser tool. It's that. It's that number, or something like it. Okay, so that's what that means. So now, if you look at the density porosity, which is always going to be a solid line because there's this kind of idea that it's kind of more real. That's not really true, but it's helpful to remember. Well, there's your density porosity. So it's going from 0 to 60. So here's 30%. It's pretty high porosity, right? Then it's kind of going around like that, and then it switches over to here. Very high numbers. Maybe it'd be best if I left it alone. But now you can see it a little bit better. All right, so that's a simplified way of looking at it. So what is the density porosity telling us so far? Does this make sense? We have a shale, and it's giving us a porosity value of, well, I don't know, around 18%. Now, is that right? Only if that's right. Now, what do we say about shale? Shale's got a lot of different types of minerals in it. It's clay, but it's also got maybe metamorphic rock fragments. It's got a little bit of sand. Maybe it's got calcium carbonate in there. So shale is almost a bad word. We like to use different, like claystone or mudstone, because shale is just another way of saying I don't know what it is. But it's probably not a sandstone. It's got some potassium in it. Okay, so it's showing a fairly low porosity, but that's because perhaps this number is not appropriate, right? But let's say that it's close. Here's our potential reservoir. This is what we're trying to decide, is that really a reservoir? That was the original question. So how is this helping? This is our density porosity. It's showing a fairly good porosity, sort of halfway in between 0 to 60, so that's around 30%. If that's true, that's really high. And that's really, really high porosity, if that's true. Okay, and then down here you can see the porosity is kind of correlating with the cleanness or the dirtiness of the gamma rays. So you have a higher porosity here, lower porosity there, kind of like you have up here. So this pattern here is kind of repeated on the section. And then one thing to note forever in your mind is that when you see two porosity curves, different types of curves, and they overlap, see how the curves overlap? Well, then what happens? What does this imply? Some people might remember this from previous class. If they overlap, you have two witnesses telling you the same thing, to use some biblical terms, right? Or legal terms, right? Then that implies that it really is a sandstone matrix. In other words, that your matrix condition is satisfied. The matrix condition. Whatever it's sandstone or limestone, that your matrix condition is satisfied, okay, whatever that is. Okay, that implies that your matrix is there. In which case, so this must be quartz sandstone. Okay, let's move ahead. What we want to do now is think about, well, what about this other type of tool? How does it work? So the second type of porosity tool is neutron porosity. The first one we talked about is based on electron density. Talked about Compton scattering. It's an active source tool like both of them. It's using gamma rays. So gamma rays in some sort of non-Newtonian sense are kind of like size-wise electrons. They're both very small. Again, Einstein would not agree with that statement, but I'm not Einstein, obviously. Okay. The other type of tool is neutron porosity. Instead of thinking about gamma rays and electrons, we're thinking about hydrogen. Okay, so hydrogen ions now are going to replace electrons as what we're trying to measure, and neutrons are going to replace gamma rays as our active source. Make sense? Okay, so electron density is going to be replaced by hydrogen, and gamma rays is going to be replaced by neutrons. So before we just start going through slides, how is this going to change our density measure? Or excuse me, our porosity measure? You see what we're doing? We're measuring something very different. If we're going to measure hydrogen ion concentration, how is that going to give us porosity? If we're going to measure a hydrogen ion concentration, why would that have anything to do with porosity?
This is kind of the opposite of the density porosity log, and that we're going to be looking at where water is, for example, because it has hydrogen.
Yeah. So if we think about, well, see, most of our electrons are in the matrix just because the matrix is denser.
Yeah.
And we can subtract out the effect of the porosity because we're assuming that's filled with something we know, water, but with certain characteristics that we can predict very precisely because we put that water in there. Okay. And so, yes, if we're looking at hydrogen ion density, well, then we're looking for the stuff that's not, so to speak. One is looking for what's there, one is looking for what's not there. You kind of get the philosophical way of looking at it. So we're assuming that all the hydrogen is going to be in the water, or oil, or gas, but we have to know which is which. We don't really drill with gas, not methane, not drill with air. So we're going to assume that we know what the hydrogen ion concentration ought to be in the porosity, and assume that there's no hydrogen ions where? In the matrix. Is that true? Depends, right? If you're talking about quartz, yeah, there's quartz is silicon dioxide. There's no H in the SiO2. But we do have some minerals that make up the matrix, again, those nasty clays, that do have hydrogen in them. So this is not going to be a foolproof method. But that's kind of where we're headed. Okay. I have to learn how to go forward on this thing. So the neutron tool is a bit more complicated. I don't want to get into a lot of detail in this for this class. It's supposed to be shorter. But we're looking at very high energy neutrons that are accelerated in formation and then decay exponentially over time. So this is showing energy levels, or scattering, if you will, as a function of time. Okay? So it's all happening very fast. You have a source of neutrons, maybe americium beryllium, chemical source that you put in the actual logging tool, and then that is putting accelerating neutrons into the formation. You start off at a very high energy level, and then there's three energy levels that we're interested in. One is the so-called epithermal. Now, what would that mean? Epithermal. That's a fancy way of saying what? Epithermal. Epi means what? Just like epidermis. It's just on top of, just above thermal levels. Okay, so that just means that just the energy level is just above the natural thermal level of matter. Okay, and then you have the thermal level. Okay, that's your average, in a sense, level of matter. And then once the acceleration dies down, then you have a third type of detection called gamma ray emission. So gamma ray is emitted when the energy levels drop to a certain point. Now, how well that works, that's a physical chemistry problem that I'm probably not totally qualified to get into too much detail, but we do in another class, but not right here. Suffice it to say, you have three energy levels. Okay, again, so you have epithermal, thermal, and then gamma ray capture. Now, I know that's a little bit sort of brief because we haven't got into detail, But the thing you need to know is that you have different energy levels that you can use for the neutron tool. Okay. Again, another class will tell you more. Check back later. So just kind of to summarize, we're using a radioactive source. It's generating rapid neutrons in the formation. Your neutrons are going to be losing energy as they collide with nuclei. And what kind of nuclei are about the same size as the neutron? Well, this thing, right? It's about the same size. Okay, so if you have a pool table, you're going to think I play pool all the time. I don't. You have a pool table and you have billiard balls and you have BBs. Well, they don't really interact. The BBs don't interact with the billiard balls too much because the BBs are like this big, the billiard balls are that big. Or a basketball doesn't interact very well because it's too big. Well, in this case, your neutrons, think back to simple chemistry, about the same size, more or less, as a hydrogen ion. Okay, so they're preferentially scattered. There's matter everywhere, obviously, but the scattering is preferentially related to your hydrogen ion concentration. So if you can find a way to detect your hydrogen ion concentration, and you assume that your hydrogen is in water, and you assume that the water is filling only the pore spaces. So there's lots of ifs, right? If all of those things are true, well then your counts per second at your detector is just a proxy for porosity. Okay, and we put the little n here just to remember that it's a model porosity. It's not the porosity. We don't actually have a tool that measures deep porosity. It's not what we're talking about today. So what you're doing is you're measuring the neutrons that return to the detectors, and that's an indication of porosity. Okay, so lower counts per second. If you don't have much returning, that means you have a lot of porosity. Okay, why? Because it's a lot of scattering going on. Scattering means it doesn't get back to the detector, it scatters away. Here's the detector, here's the source. So you have lots of these things, and you have lower counts because it's scattered away. Okay. So hopefully that makes sense. So the simplest way to think of a neutron tool, I once went to the office of Halliburton in Vernal. It's closed now, but the guy I asked him to explain how the neutron tool worked. So instead of going through all this sort of stuff, he just said, it's a hydrogen counter. Like, yep, okay, that works. There's a lot more details. But if you remember one thing, it's a hydrogen counter, and you're hoping that the hydrogens are all just going to be in the pore spaces, and then you have the porosity. So here's what could be a classic neutron porosity log. Now, these logs are always run together, or these ought to be, unless there's some weird reason not to be. Now, I think I mentioned last time, you got to be careful. You have an LAS file. It's a file that shows all the logs that were collected. Some of the logs should be used in this class. I think Bill counted them up. He's good at interrogating the data very carefully. I think he said it was like 200 logs. Now, you may decide to just load the neutron porosity log and not load the other one. Well, that would be a mistake, okay? Because both logs are shown here. You might ask, well, this says porosity units neutron, so that makes sense, 45% to minus 15%. You can understand the negative numbers. But what does this represent? Bulk density, that's for the density porosity log, or this one, right? And this is from the N phi versus D phi. Okay, so that's from the neutron, this is from the density. Why is this? How do we use these units? See, the scale is such that we can simply read off for the density porosity log, which is shown here in the dark line, the porosity units. They're scaled together. Makes sense? Now you say, how are they scaled together? There's some information missing here. What's missing? Otherwise, we don't know how to scale them together. It doesn't. We haven't been told the matrix. And I got this from another source, and I don't know if I didn't copy it. I think it's not actually included. It's actually sandstone or quartz made matrix condition. But that allows you to go from density, which is the actual measurement, to porosity, which is your model measurement. Okay, does that make sense, or have I confused you? This can be a little bit confusing because, like, well, but where's my porosity? Well, it's here. They just use the word neutron. So so they don't have to put two porosity scales, which ended up being the same. Okay. So, can somebody explain this log? Now here's the lithology. So this is an unusual case. We know the answer first. Now a geologist is going to look at the dots and think what? What do the dots represent? Sandstones. That's quartz sandstone. That's a bunch of quartz grains. Silicon dioxide with porosity. Okay, that's what that is. They took a core. It must have been interesting. This core is not cheap, so there must be something interesting about this, because this is a real case. And then what's this supposed to represent? This is shale, probably. Okay. In fact, it's not probably, it is shale. Okay. So can you explain the log? Or just what do you see? We got them labeled here. So here's density porosity. The dash is neutron porosity. What's the first thing you notice?
Crossover.
Well, yeah, they're not the same. It's like, I remember the first time I was assigned to do some kind of work as a graduate student, and it's like, well, you need to find it. I was doing gravity surveys. Nothing to do with, I don't care about logs. I'm not interested in petroleum at the time. So I go and get a density log. Well, I'm going to get the density, and I'm going to get the porosity. And I look at the curves like there's two curves. Which one's right? Do I average them? Do I go eeny, meeny, miny, moe? How do I tell which one's right? Okay. Well, there's a way to answer that, but the first thing you notice to make yourself more frustrated is how they switch over. Over here, the neutron is high, and the density is low. But what happens here? It's just they crossed over. Okay, so that's a term that's used a lot in crossover effect, because this might be considered more normal. Maybe this is more normal. I hate to use the word normal because nothing's really normal, but more usual perhaps. But if I have a separation here, or crossover, before we just jump to the answer, what does it mean? Something's wrong, right? There's an assumption that's violated. So what assumption has been violated? Now I'm telling you that this sandstone matrix has been assumed. Okay, so we know that. So that's correct. So that's this for the density porosity log. And likewise, we have the correct matrix assumption for the neutron. Now it's harder to write that down, but that's correct. So the matrix is right. So this is a sandstone, and it's a sandstone matrix. Now what did I say? We expect the two curves to overlap if the matrix condition is right. Now I'm telling you the matrix condition is right. So what's missing? Why did I lie to you? Why don't they overlap? Something else must be wrong. Well, what are the two things that we assume? The matrix and the fluid. Well, what's that? Well, if it's water, the density of water, fresh water, is something like that, 1.00 grams per milliliter. What if it's not? How could it not be water? What else could be down there?
Oil or gas.
Oil or gas. Now, oil is different density, obviously. It floats on top of water, but it's not hugely different. It's different, okay? But what's really, really different? Gas, right? Methane is way, way, way lower density. It's 0.000 something, some number, okay? It's really quite small. So this is actually a gas effect. Okay? It's a classic example of a gas effect, okay? So in this case, you have this type of separation. Now that you know it's gas, I'm telling you it's gas, it's methane. The methane is displacing what in the pore space? It's displacing water. Maybe it's displacing oil, but it's displacing something that originally is a lot more dense, okay? So can you explain why the neutron tool is so low? It's separated or crossed over, depending on your favorite word. Why is it so low? I mean, it's a difference. See, here's 15%. And so it's like 10-ish. That's a lot, okay? So why is it so low? Because we're expecting this, right? We're expecting it to be water. But if it's counting hydrogens, it's expecting to count the amount of hydrogen you expect in water. Now, do you have the same amount of hydrogen in a jar of water versus a jar of gas at normal pressure? No, you have a lot less, okay? So, And again, it's a hydrogen, it's counting a lot less hydrogen than it expects. So it's translating that hydrogen, assuming that it's water, but it's really gas, into low porosity. Make sense? Okay. This is sometimes called a crossover effect. I don't actually like the word crossover, some of you will know. I prefer the word excavation effect, which sounds a little bit, crossover is what you see on the curve. It crosses over. Excavation is the process actually happening in the pore spaces. So what's excavating what? The gas is excavating the water. Okay, so you could call it pushing out effect, but excavation effect is one that gets used in literature. So you got to be careful. The word crossover or separation, that's just describing what you see on the log. There's lots of different words for that. But the process is excavation. It'll help you remember which way the curve is supposed to go. Okay, so that's a classic gas effect, and there's your symbol for gas, and in fact it is indeed gas. So here's another log. I think this is from your textbook. The reason neutron and density logs are run together is not just to find gas, but because they can give you information about the lithology that you can't just get from the gamma ray. Here's our gamma ray curve. It's a nice looking curve. It's the purple one, right? So yeah, that looks very clean. That's looking dirty, sort of serrated. You might call it ratty. It says shale sand, shale sand, shale sand. This is looking nice and clean. Maybe it's a reservoir. Maybe it's anhydrite. Don't know until we keep looking at other logs. And these are the other logs you want to look at. Okay, if you just had this, well, all you know is clean versus not clean. You're tempted to say reservoir versus not reservoir, but that could be very, very wrong. Okay, you can make a very big mistake. So this is our, we just looked at one of these, right? So the dashed line, again, even though service companies are extremely competitive, I mean, they're really, really competitive, they cooperate on a lot of symbology. I said this before. And one of the things they cooperate on is that the neutron porosity is always dashed, maybe because it's a little bit abstract. I don't know. And the density porosity is always the solid line. Not always the same color, but solid versus dashed. So this is your excavation effect or crossover. I'll keep using the word crossover because it's out there. If you go to Google crossover gas effect, you'll get lots and lots of stuff, probably less if you type in excavation effect. But it's an excavation effect that's happening. Okay. So that makes sense. So why is this low? We're going minus 15 to 45, so 0 is right here. Why is it so low? Because you're assuming that it's water, but it's really gas. So the small amount of hydrogen looks like low porosity. But that's because you used the wrong number for your hydrogen index. Okay, so that we understand. Now what about these? Now, can you explain these? These are not crossed over, these are the other way. So if we're going to reserve the word crossover for gas, maybe we've got to come up with another word for when it goes the other way that doesn't match. Maybe separation. It's just a word, okay? So these are separated, and these are crossed over. So how can you explain that? So the first thing you might say is that well, the matrix condition is not satisfied. The matrix condition here is, by the way, it's quartz. Okay, but the matrix condition is not satisfied, or the fluid's not satisfied. Now let's just say that I'm going to tell you that the matrix condition is not really a problem here. It is, okay? Or is it? Okay, the matrix is okay here, but here it's a little bit off. How could it be a little bit off? Instead of having quartz, maybe I have some kind of shale component. Okay, so if I had shale, this is more for the geologist. Shale is made up of what type of mineral? It's clays. And if I showed you a chemical structure, which I won't do, you can look it up if you want for clay, you would find lots of hydrogen in the clays. You'd find two types of hydrogens. Not two types, but two environments. What we call bound water. So there's two types of bound water, or ways we think of bound water. Water that's mineralogically included within the crystal lattice of the clay. So you have that. If you're an engineer dealing with swelling clays, you know all about that. Okay, you could probably tell me about it. And then there's also just water trapped in the pore spaces that is not effective porosity. Because if you have porosity that's not connected, what's going to happen? it's not good for anything if it's not connected. It has no permeability. Okay. So what you have here is what? It's showing that our hydrogen counter is really high here and kind of high here. And what type of rock? If I tell you this is a sandstone, and that the dirty gamma ray is shale, well, then what type of rock do I probably have here? So this is probably shale. It's got clay in it, and that clay has bound water, and so it sees extra porosity. Make sense? It's seeing extra porosity because it has this bound water that has lots of hydrogen in it, but it's not real porosity. It's just hydrogen is within the mineral structure itself. Okay, so these cases here are cases of bound water effect. Now, again, in the other class, we go into a lot more detail. I probably should stop saying that, but that burns it for next year, perhaps. But this effect here can give you another way to think about shales, how to identify shales. Okay. So here's an exercise. So here's another log, taking this from another class that I used that might look familiar to some. So can we interpret this log? So what do we got? We have gamma ray. Here's our curve, 0 to 200. This solid line is gamma ray. We don't have our electrical resistivity. We've taken that out just for educational purposes. Here's our porosity going from -10 to 30%. Now, what's some important information on this log display? What about the matrix? It's a limestone matrix. Okay, so we need to know that. That's important to know this limestone matrix. So it's calcium carbonate matrix. So you see that the log, the two porosity curves, do they ever match? They don't actually ever match except when they just cross over briefly and when they intersect. So let's look at this one right here. What do you think that might be? The neutron porosity, as usual dashed, is showing a very high number, and the density porosity is very low. So what must that be? If you see an excess of hydrogen being counted, that might be a shale. Okay? We're going too fast with that logic. Now, what do you look at for the gamma ray to ask, is it really a shale? Well, right here, it's showing a fairly hot number for the gamma ray, and that's correlating to a peak on the neutron tool. So the neutron porosity is counting hydrogen. That hydrogen is bound to water within the shale. So once you see that effect in one place, you can recognize it in a number of places all across the log. Here's another one here. Notice high number for gamma ray. Here's this peak here. And then there's another one there. These peaks are matching. I think I've marked a few others. Okay. Now, what about, so we got that. That's the bound water effect. Okay. Now, what about this? What's going on here within the red rectangle? Now, this is just the opposite of this. This is not crossed over. This is separated. Maybe you could say. Well, actually, it is crossed over. This is separated. This is crossed over. So the words are kind of not very helpful. But they're not superimposed. Do we have something that's clean here? So it's clean, right? And then over here, well, it's not really great porosity. Here is 0. Right here is 0. Let's just draw our 0 line. Like, I didn't very good job. Okay, but that's sort of 0 line, right? So this is showing that they don't match. It sort of looks like gas, but here's the gotcha. You could also get a gas effect if the matrix condition doesn't work. So this is assuming limestone, but without going into more detail, what you actually have is a sandstone. Okay, now this is probably too much detail for this level in the class, but the moral of the story is not all crossovers are gas. This is a big mistake. I've actually seen mistakes like this in like the flagship journal of the American Association of Petroleum Geologists. I used this in another class, where I show a mistake where they didn't recognize that the crossover is not simply a matrix, a false matrix assumption. Okay? And these were people probably smarter than me. They got a paper in a prestigious journal. They made this mistake. So I'm telling you, don't make that mistake. Understand that the gas crossover effect could be just a matrix condition, and that's what you have here. That's actually sandstone. So what else do you notice? Here's a funny looking part of the log, right? Funny, not ha-ha funny, but it's irregular. So what is its effect here? Let me trace this out. This is the density that I'm drawing, and then it swings all the way over here. These negative numbers. It's actually backed up. This is a backed up curve. So if this is minus 10, then 15% is over here, minus 15%. So what could cause this? What causes the density tool to go negative? It has something to do with the assumption about the matrix. If you have a matrix that's much higher density than what you assume, then this is going to go negative. And so that's probably the mineral anhydride. Now you say, well, how do you know that? Could be a lot of things are dense. Well, what do you notice on the gamma ray? The gamma ray shows the cleanest rock on this whole log. Okay, it's got no potassium. Because what did you say the chemical formula for anhydride is? It's got calcium, it's got sulfur, it's got oxygen. There's nothing that produces gamma rays. Okay, it's not very much. Okay, so that kind of backs up the idea that it's anhydride. So let's look at another one. Here's another log. This is a little bit easier. Same type of logs, limestone matrix, gamma ray. It's the neutron density combination. The solid line is density porosity, dashed line is neutron porosity. What's the first thing you notice? They're superimposed. So when they're superimposed, what does that mean? That means the matrix condition is satisfied. So if you're trying to interpret a log, and you look at your porosity, you've got neutron density, and they are together, well, now you have a magic bullet. You just look and check out what was the matrix condition, and it was satisfied. Now, there's ways to actually make that not work, but that's going to be correct most of the time. There's always a gotcha somewhere, and everywhere there's a gotcha, but we'll talk about that, okay? So this is applying, you have a limestone matrix, and basically the rock is limestone, there's no sandstone in there. Okay. Now what else do you notice? There's little bits and places where it's separated, but there's little bits maybe of sand in there. So this tells you that you have little bits of sand, if you understand how to interpret which way it separates, which we talked about before. It could look like a gas effect, but it's actually just a matrix condition. But what's the big thing? What's the gorilla on the log? So here they're more or less the same, and then right there, what happens? They're way different, okay? Way, way different. It's zero, so what it's showing is fairly tight rocks right here, and then they get very, very different. So what does that mean? What's the first thing you say? If two logs are different, then it cannot be limestone unless you have something going on with the fluids. Let's say that the fluids are behaving normally, and in that sense there's no gas. So this is a hard one because you have to have some other information, but it turns out that it's not a shale, because what did we say that if you have a high hydrogen counting, that could be shale, right? Now is this shale? You look at the gamma ray. It doesn't look like shale. I mean, there's a little bit of shale there, maybe, and there, there, and there. But overall, it looks very, very clean, cleaner than anything else. Turns out it's a matrix condition, again, that's not satisfied. This is actually dolomite, okay, with little bits of shale in there, okay. So how would you actually know this? And of course, there's some anhydride in there as well. You notice how it goes negative. So the way an interpreter would deal with this, you might be saying, well, how do you know that it's really dolomite or sand? Just because of the curve separation. You would use an algorithm like this. This is a graphical version of an algorithm that has the bulk density plotted as a function of neutron porosity. And then these are different matrix conditions. And so if you plot your density, in this case like 2.6, and then you have a neutron porosity of 20, well then that implies that you have a dolomite or dolostone, same thing, matrix. So that's how you actually go and decide what the curves mean when they're separating, and it's not a gaseous bed, you can use a transformation like this, sometimes called a cross plot, that's plotting one thing against something else. Okay. So let's do another test. So here's a log that's got gamma ray. GR stands for gamma ray. So we got some variation here. Someone's gone in and colored it. Decide, well, I'm going to say everything to the left looks reservoir-like, assuming that it's not anhydrite or salt or something that's just clean with no porosity, but possible matrix and possible reservoir, and everything to the right is going to be uninteresting. And then the rest of the log looks like this. And the question is, can we explain these relationships? So let's take an easy part. So these are the two porosity logs, right? So the dashed line again is neutron porosity, and the solid line is density porosity. The SS stands for what? Sandstone. So a sandstone matrix is assumed. So what you might do, you say, oh dear, they're all different. I think I'm going to go to the easiest place first. Where's the easiest place on this log? Right there. Okay, they're sort of close together. So I'm going to decide if this were a classroom where each person had to we just went through the classroom and each person picked a part of the log to explain, and you've got to be the first one to go. You pick this one, right? Oh, that's easy because they're superimposed. So they're close. They're not totally, but they're pretty close. It's a linear, it's not a log scale. So if they're superimposed, it means what? It means that the matrix condition is satisfied. So we'd say, well, this is probably quartz, right? Now, how would you back that up? How would you make say you're an investor, and if this is quartz, then maybe it's worth spending some money completing the well and seeing what comes out of it. So you're going to care because you're going to spend $10 million towards this well. So you kind of care about this, right? So what are you going to do because you care? Well, if you might look over here, it's showing clean, right? So that's consistent with it being quartz. Because quartz is just silicon dioxide, there's no potassium, thorium, or uranium. Like, okay, I'm starting to feel better about my $10 million investment, but not totally. So I got this purple curve. What's that? PEF. D/E stands for Barnes per electron. Okay. And here's 10. So if this is 10, that's 10. So what's this number here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So 1. It's sort of 2-ish. So what type of, that's the PE is about 2. What type of mineral is that? Well, quartz is 1.8, but how can it be 2? If we add fluids, that makes it go down, not go up. So if it's just pure quartz, how could we get it to be 2? Who remembered the one for calcite or limestone? What's that?
Limestone is 5.08.
Right. So you see where I'm getting at? What am I looking at? It's not really just quartz, because I have grains of quartz. Here's my attempt to draw grains. Okay, so is that a perfect representation of the rock? With something holding the grains together, right? Not totally. But what's this other stuff in red? Oh, cement. What's that made out of? Oh,
Calcite.
probably calcite. Very common. Why? Because calcite is more soluble. It's very soluble. It dissolves, dissolves very easily to weak acid. That's why you have caves and limestone blocks. Okay. So what was the PEF for calcite? It's about 5-ish. So you have a little cement in there, drives this number up. Because this is a bulk number. It's not looking at one particular grain, it's looking at the bulk, obviously. So, $10 million. For $10 million, you want to think about these things. So I'm feeling pretty comfortable that this is a quartz sandstone. Now, whether or not it has oil in it, well, we haven't got to that part yet. We need another log. So I picked the easy part. All right, now who wants to pick this part? Should I do it? You can watch me. So what do we have? we've got the neutron being higher and the density being lower. Where's 0, by the way? Well, 0 is right here. Okay, so there's a 0 line. So they're separated. So if they're separated, they cannot be the matrix condition, right? Unless the fluid's wrong. Okay. So what type of rock do you think we have here? We have excess hydrogen, because we have the hydrogen counter counting a lot compared to the density tool, which is solid red. So that could be a shale. That's my hypothesis. Let's say shale is valuable. It's starting to get that way. It's unconventional. What would I want to see with the shale and say the gamma ray? I want to see a high lower number. Here's my scale. I want to see a high number for shale because I expect shale to have a lot of potassium in it. And that's kind of what I'm seeing. It's not real high, but it's certainly looking dirty compared to my clean rock over here. Okay, so that seems to be consistent with bound water effect in the shale, and I'm getting kind of a high gamma ray. So that's all consistent. Now what about the PE? What's the PE telling us? So there's 0, 1, 2, there's 2.5, 2, 2.5. Is that useful? Tone of my voice kind of gives it away. I'm not a very good liar. I'm not a very good game show player. I lose. Okay. Shale's got everything in it, right? You can't draw a shale like that. You have to have like 10 different symbols. Okay, so the P doesn't help us with shale. So that looks like a bound water effect. And once you decide that's a bound water effect, you can go looking for it. Well, here it is again. Yeah, you have high gamma ray, low deflection. And this is really telling right here. What about this? Very nice example of what we're seeing. And again, what happens to the gamma ray? It goes high. So I'm feeling pretty confident that that's a bound water effect and that's shale. Now, is there anything else left on here that's interesting? So we got this one. We've got this. Well, here's coal. We're not going to talk about that. That's weird. Okay. What about this? This is a little different. I actually have the answers here. In case you haven't noticed that. So they're saying limey dolomite. What does that mean? That means it's dolomite, which is mainly calcium magnesium carbonate, but it's got a little bit of calcite in there as well. There's reasons why that's quite common, which we won't go into. And what that is showing is that, remember, you had this kind of separation that looked like shale and dolomite, and that's what you're having here. And the reason they made this, the reason interpreters said this, is because you have kind of a clean gamma ray, and you wouldn't expect a clean gamma ray with the shale, but you have this separation. So the only way you can get that separation is if you have a matrix condition being violated. Okay. So that's kind of a lot. You see, again, what I want you to get out of this is that you have to know the matrix condition in order to make sense of your separations and your crossovers. Otherwise, your porosity tools are actually just going to confuse and confound you. But if you understand why they separate, then they can actually lock in the lithology, particularly since you have the PE effect, okay, to look at. I think this is the last one. So that's good, right? So here's our log again. I had this question before. I just showed this a few slides ago. So my question is, does this make sense now? Is what makes sense? Well, there was one interpretation that was done. It makes a little bit more sense. Here's our neutron porosity tool. Now, can you explain this now? When I first showed this, I hadn't talked about the neutron tool. Now, what do you see? Well, everything is different except where it isn't. So if you pick the first place to try to understand, where would you pick? Tell me where it's on. Right there, because they're kind of the same. They're superimposed. One curve's more nervous than the other, but they're superimposed. So then that tells you what? They're superimposed, so what must be the case? The matrix assumption must be correct. So it's sandstone. Now you're still not convinced. You want to look at other logs. So what do you look at? Well, there's no PE log. They don't have it. Okay, it's not there. That's just the way it is sometimes. Okay. So would we expect it to be clean or dirty if it's sandstone? Well, it's quartz, so we expect it to be clean, and it's looking pretty clean right in there. Okay, the gamma ray tool is showing a high deflection or low value for API gamma ray. So I picked the easiest one, right? Now, what about up here? Let's go to the top. Here we'd say they're separated. They're not crossed over using the lingo we established. They're separated. Okay, by a lot. Okay, so you see the separation in here? So it can't be that. It can't be sandstone. Okay, well, what do you often have with sandstone? Like Gulf of Mexico, typical example. You have sand and you have something else. You got sand, something else. What's the something else? Shale, right? Well, that's how these people interpret it, shale. So this is shale showing relatively high gamma ray. Here's your scale again, high gamma ray or low deflection. So it's moving to the right, it's not deflected to the left. So that seems like a bound water effect. So here's bound water effect. So far we got two characteristic relationships. Bound water effect for shale, superimposed logs for matrix condition being satisfied. Is there anything else on here that we can cite as a textbook example of something? Here's one. Here's one. Anything else that you see on this log that would be a missing hint? It's a textbook example of something.
The crossover effect.
Yeah, the crossover, right? And why do we say crossover? Because this has crossed over from that, right? And that's often the case because you think about a reservoir. So you've got this big column, right? You got water, then it comes in contact with what? You hope. Oil, and then what's on top of that? And then what's on top of that? A seal. A seal. Shale is a really good seal. High porosity, maybe, yeah, often, but low permeability. So shales can be pretty good seals. That's why they make terrible conventional reservoirs, but potentially great unconventional reservoirs, okay? So this is a pretty classic type of pattern, right? That you go and you find something where, well, this is just sandstone, and what is the fluid in this particular case? Well, it could be oil, could be water, not a lot of difference between the two. And then we start to see this effect, these crossovers. And then on top of it, finally, the separation. These are your shale effects. These are your shale effects, but here's your crossover. So what you have is some compartmentalization. Here's your seals, okay? Here's reservoir, and here is a reservoir with gas. Okay, so there's kind of your geological interpretation of it. So this could be, I don't know, this could be oil. We need to have some other, we need to have electroresistivity along. Because the pushing out of water by oil is not going to change the fluid condition all that much. I mean, it will, but not enough to make a huge difference. But certainly gas will. Okay. So what is the so-called answer? Okay, so this is one person's interpretation. They're just measuring the crossover in terms of percentage. So separation is a word that's reserved for this type of pattern, a shale pattern, a bound water effect, crossover, 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 back to separation, shale effect, and then here they have neither. They're superimposed. Okay. So does that log make sense? Could you go and do that if you had it on your own? Question?
If it's superimposed anywhere on the log, that confirms the matrix assumption?
Yes, most cases. There's always the gotcha. So yes, usually if the two are, I'll explain my hedging in a bit. If the two are superimposed within the matrix condition is likely to be satisfied. Now there's always a gotcha. What do you think the gotcha could be? So I'm saying if it's a sandstone matrix and I see them superimposed, like, well, that means it's mainly just quartz, silicon dioxide. Now nature can be kind of unkind sometimes, right? How can nature be unkind to us? So that is not correct. You have to almost think poetically. Well, what if it was not sandstone at all? What if it wasn't just calcite? What if it was calcite and dolomite together? That could actually produce, they cancel each other out, right? Because the dolomite effect goes this way, right? And the calcite effect would go the other way. And if you had certain right amounts of each, then they would move this way and then stop and be superimposed. I can't prove that. I'm not ready to prove that to you. But you can get superpositions when you have kind of a nightmare scenario where you have the matrix. You have two rocks, two minerals, neither of which are the matrix, and they cancel each other out. So yeah, there's always a hidden gotcha. There's always a possible unkindness by nature to make that superposition not actually the matrix. But most people would feel comfortable. How would you do that? So how would you actually satisfy yourself that unusual situation is not the case? You ask for another log. What other log would you want to see? What's the simplest thing you could ask for? That could be like a test question. You're investing, right? You had my class. You've learned so much. You retained it over 10 years. Now you're a rich dentist. You somehow became a dentist. That's why. Okay? You have lots of money to invest. And you remember, and if somebody shows you this log and they're kind of like just oiling their way through it, kind of slick, not oil in terms of reservoir, but oil in terms of just slick talk, all right? And you say, well, is there any chance that you could have a compensating effect of dolomite and calcite to make that superposition work and not actually sandstone? You would really impress the person. But that would be a very in-depth question. So that's kind of a roundabout way of looking at your question. But when they are superimposed, it's a pretty safe thing to assume that the matrix condition is satisfied. In my other class, you might remember that I showed some nightmare examples where they actually are superimposed, but it's not sandstone. There's no sandstone anywhere to be found. It's just that they compensate each other. If it were a more detailed class, you could have a math problem where you actually figure out how that would work and do actual numbers, but we're not going to do that. I think that's the last slide. We still have some time left. If there's any questions, or I could talk about where we go from here. Bill will talk about what he wants to do next on Tuesday. Other types of logs. There's of course, we can talk about all of them. There's a third type of porosity log that we may talk about. We probably will, called the sonic log. So the word sonic is actually kind of a trade name, because it's not affiliated with the restaurant chain, as far as I know. Might be called acoustic log more generically, and it measures the travel time along the borehole as the tool is coming up. It has a transmitter, a little receiver, like a little seismic survey. So transmitter, receiver, it just measures the speed of sound in the rock right next to the borehole, and that can give you porosity. Okay, so we actually use that tool, not so much to get porosity, because that's not a really great tool to get porosity. You see why it is? Can you draw a picture in your mind? Why are we measuring the speed of sound right along, if this is the borehole, this is the hole and this is the rock, I'm measuring the speed of sound right here.
Well, if you have fluids in there, depending on the fluid properties, it'll alter the speed of sound.
Right, but you know what the fluid but you know what that fluid is because you put it in there.
Oh,
So that's actually a good thing, because you can account for that, just like you account for it here. But I'm wanting to measure the natural porosity. There's my head. As always, I want to measure the real porosity.
See.
But I'm measuring a sound wave that's literally traveling this far into the rock. What's wrong with that?
Porosity.
Hmm?
Drilling, is that right?
Yeah, well, you drill a hole, it hurt the rock. it just doesn't it's just not inert, you fracture it. And of course, when you inject fluids under pressure, well, what's that? Fracking is doing exactly, creating more porosity. And sometimes you frack a rock unintentionally just because you have high pressure mud. You don't use the word frack in that case. But that's not the greatest tool for porosity, for that and some other reasons. But it's a very good tool for something else, and that is relating your log, which is the depth, to your seismic data, which is measured in what? Time. And that's where we're going to go to next week. So the key log for translating from depth to travel time is the sonic or acoustic porosity log. Not so much because of porosity, yeah, it measures porosity, but because it gives you speed of sound, it gives you velocity. We use the word velocity, it's technically, velocity is a vector. We ought to be using the word speed because we never use vector, well, we do sometimes, but we're not going to think of velocity as a vector in this class. So we ought to be using speed, but we're going to use velocity because that's what everybody uses and it makes it sound smart. Okay. So that's the use of the sonic porosity, the third type of porosity log. And so we're going to wait till we talk about seismic data a little bit, and then I'll come back in and talk about how you use the sonic porosity log. Not so much to get porosity, because it's the lousiest porosity, but to actually correlate depth to travel time. Because if you have a seismic section and you see an event that's like the top of a reservoir, here's Bill's very nice block diagram. If this is the top of your reservoir, where my finger is, well, there's not a scale on here, but if there were, it would be in travel time. So you say, well, the top of that reservoir is 1.39 seconds. What am I going to do with that? You can't tell the driller, go down to 3.9 seconds, right? You have to use velocity because here we have a depth. If you have a depth and you have a velocity, you can put those two numbers together and get a travel time and back and forth, right? So that's really what we need to do next with logs is like, okay, it's great to have log, but how do we put our log on or in our seismic data? Where does it go? Seismic data is in time, this is in depth. So the sonic tool actually does that. Okay, so we'll talk about that whenever Bill wants me to do something. And so again, I put this PowerPoint's all just one big horrible PowerPoint on a flash drive in the geology office. So if you want to get it, you're welcome to look at it or whatever, or load it or whatever you'd like to do. Okay. I don't post things on Learning Suite or something like that because I'm trying to stay on the right side of copyright laws. Okay. So, all right, well, thanks for coming. And Bill will be back. And as I said before, Bill is easily the best person, probably in the state of Utah for certification, but even beyond that.